Okay, if we have a charge here and we want to find the electric field at a point here due to that charge, then that electric field, by the definition, is in the direction of the R vector. Right? Because you multiply by the R vector divided by its magnitude, and you're multiplying KQ over R squared by that vector. Well, that vector is radial, right? Means the line of the vector goes through the charge. It's radial with respect to the position of the charge. Okay? So we have this. Now, and of course, if the charge is negative, it's going to be toward, I can only draw one. Don't want to confuse the issue with two possible electric field vectors. So just assuming a positive charge, there's your field. If it's a negative charge, it's toward the center. Now, if we got, and we're talking about now, we're trying to find the flux of the electric field over the surface of a sphere. Okay? So we imagine we have a sphere, we've got a little area increment. Okay? So that'll be a surface area increment, which is the area times the unit normal. Okay? And the unit normal, of course, is in the same direction because normal to a sphere is perpendicular to its surface at that point. Perpendicular all tangent lines. Okay? So that now the flux is E dot ds, right? Which is just and I'm going to say the magnitude of the flux so I don't have to worry too much about this. It's the magnitude of the electric field times the area of that increment. And this is because your normal dot with E is either going to be equal to the magnitude of E or the negative of the magnitude of E, right? So the magnitude of E dot N is just E, magnitude of E. Okay? So there we have the contribution to the electrostatic flux. And of course, I'm assuming we know what flux is because we've all had multivariable calculus more or less recently. Okay? So what's the total flux over the surface of that sphere?